happy to introduce Dr. Zhang. Please come forward to talk about the first live birth.
So again, forgive my broken voice, and the good news is today is slightly better than yesterday. I have to weather forecast my voice every day. So it's been a great pleasure to have friends came from all over the world and discuss the subjects of our common interests. So welcome, everyone. And so far, I think we had a great time. And I will spend the next half an hour to discuss about what we have done, and it's kind of like a quick review about the nuclear transfer technology and give some a little bit of update. And some of the information we're going to present in the American Society for Reproductive Medicine on October 19th. So to be fair, I need to restrict some information to be presented in the ASRM meeting. But I think we have enough things to share with you and to bring some questions and discussion. So you can stop me anytime, and so I can take some questions. Otherwise, I would like to start some data and to share with everyone. So for the nuclear transfer, we know that we can perform the nuclear transfer in the different stage. We can transfer in the different stage. And we can perform the nuclear transfer at the germinal vesicle stage. And we can perform embryo transfer in the spindle stage, which will come back in a minute. And we can do embryo transfer in the pronuclear stage. As of 2015 and earlier, our major attention was on the nuclear transfer on the pronuclear stage or GV stage, and for two reasons. For the GV stage, it may help to correct or rescue some of meiotic error at this stage. And for the pronuclear stage, it's just for the previous technique difficulties, because many years ago, due to limits of technology, the human spindles is not so easy to visualize. So nuclear transfer can only be performed easily at germinal vesicle stage and pronuclear stage. So now I think the time to continue doing pronuclear transfer will be phased out. So far, we really cannot think there are any clinical relevance. We have to do pronuclear transfer, even though in a certain circumstance, maybe pronuclear transfer is better than spindle transfer. But technically, spindle transfer now is possible. I just want to show you some animation to kind of explain how all this technique works. If you don't like the music, let me know. We're actually looking for the better music. Three different types of nuclear transfer. First one, let's discuss about spindle nuclear transfer. So donor, patient, and husband. Patient egg, donor egg. Spindle, spindle. First part is enucleation to remove the spindle. And second part of the procedure is a delivery of the removed nuclear spindle into the perivalvular space. And next, a difficult part is fuse the spindle into the host nuclear. So this is a spindle nuclear transfer. To save the time, I'm going to play germinal vesicle transfer and pronuclear transfer together. So we're going to play these two together. On the left panel, we're going to show germinal vesicle transfer. In the lower panel, we show the prenuclear transfer. In a very similar manner, the nucleus, either pronucleus or germinal vesicles, are removed. Again, in a similar fashion, they will be delivered into the perivitally space. Again, next step is electrofusion. Okay, anybody know? First of all, anybody likes music? Don't be polite. Number two, we have a quiz. If you can tell where the music comes from, and then we don't have a prize for that. I'm sorry. Very good. David keeps absolutely correct. Oh, okay, Dr. Arthur can figure it out too. Okay, so we are very familiar with this number last few sessions. So this is very much to show same number again, just to justify what we are doing from our clinic. As you see, with the increase of the age, with the increase of the age, the percentage of the embryo will show the blastocyst stage is decreased, and the embryo show the euploid embryo decreased significantly. Ongoing pregnancy rate decreased. And looking from a different angle, the number of the oocytes you needed to create one live birth baby from less than 35 years to about 4x, and sharp after age 42, you need a 31x to produce one live birth baby. And this data is very similar to Dr. Kato presented yesterday from Japanese group. So this all indicate that there is an increase of defect of the age-related defect in the human eggs. And this just show again from different stages of the egg with the increase of age, and you need more and more eggs. By the age 42 to 43, you actually need 31 oocytes to produce one live birth baby. So the aneuploidy rate, as I showed yesterday, is about 91% of embryo will show abnormal chromosome numbers. So this is one of our favorite slides, trying to explain what's the mechanism cause increase of aneuploidy in the embryos. And now we all agree that the error started mainly during the first meiotical division, and these spindles cannot have an even distribution and cause a so-called classical non-disjunction, and this just show different kind of non-disjunction. And this is a very classical slides, and we've been presenting these slides for numerous times because during the war, so many study was done since then from 1996. As you can see, this spindle structure start to change in the egg from Asian women, and the metaphase starting to be disorganized. So this is all happened during the meiotic era, and I think this is the basic foundation of our work. And to better understand this situation, Dr. Liu and I created this in vitro model by aging the mouse oocytes by prolonged coach in the IBMX to hold the GVBD and let the cytoplasma to be aging. Then we start this reciprocal nuclear transfer work. And as you can see, this is what happened after the egg going through in vitro aging and show chaotic metaphase 2 spindle and metaphase plates and spindle. This is a fresh control. Now, in sharp contrast, following germinal vesicle transfer, the reciprocal transfer to bring the GV from the fresh egg into the aging egg and vice versa, to bring the aged GV into the fresh nucleus, and you can see you can bring an aging GV, which not real aging, it's from the aging eggs, into the fresh cytoplasma, then go normal alignment. Beautiful. And vice versa. If we bring the GV from the aging oocytes into the fresh oocytes into the aging oocytes, and it shows a very similar manner as in the in vitro aging egg. So this draw the conclusion, very important conclusion, is that to a certain extent, the meiotic error in the human oocytes are definitely controlled by cell machineries in the cytoplasma. And to a certain extent, it can be rescued by host cytoplasma. So this is a two very important conclusion. Third conclusion is that it seems there's no rejection like a human organ transplantation. You worry about immunological rejection. They are readily accept the falling nuclei into their own eggs. So this is a couple of very important findings. The next question is that, so whether these eggs are really can make babies. So this is just more data to show in the different combination, which I'm not going to discuss in more details. So this is a very similar study we did in human eggs. It's a GVX, it's donor, and the donor, and donor, and donor, and the exchange, and the refusion. So this study just want to show the safety of this process. And from this, after we show that in the human GV egg, the same performance can be accomplished, then in 2008, and we started working on to see if we can actually using this kind of model to create a live birth in mice. So the idea is to get the GV exchange with the GV donor, and you create a new egg, and do in vitro maturation and fertilize egg and make embryos. Here's the problem. Yesterday, we spent a large amount of time to talk about in vitro maturation of oocytes. And our colleagues showed beautiful data. We can grow the preovulatory oocyte from primordial germ cells or from primordial follicle. But real question is, can they make live offspring? That's the key question. And we all know that human oocyte maturation in vitro is still may not be as efficient as in vivo eggs. So we take this mouse model, and this study was done many years ago by Dr. Liu and me. So as I just repeat it one more time, after germinal vesicle exchange, in vitro maturation, in vitro fertilization, produce cells. But they all had a two-cell product. This embryo cannot make it to the blastocyst. So we know that one of the first obstacle in the nuclear transfer for the germinal vesicle cell embryo is how to mature this egg properly. So we did this alternative study, and this is called sequential nuclear transfer. So first, let me describe the technique, see if I can make this clear in 1 minute. So we already familiar with this part. Remove the GV, let's say from the patient, put into the host GV, let's say from the donor, and we have a reconstituted oocytes. I did not create these words, and these words I give the credit to Dr. Jack Cohen, and come out, he said, it's called reconstitution, probably sounds much better than restructure. So this spindle, after in vitro maturation, we take the spindle out and transfer to the second egg. This egg is in vivo mature oocytes. Then we do in vitro fertilization, have a live birth. And this work is done as early as 2003. So technique is available since 2003, and we can do sequential transfer, meaning that one nucleus we can do 2 embryos like a multiple rockets to launch the satellites to the orbit. So this is a very, very powerful tool, and it's a very, very useful platform. So the conclusion from these slides is that nuclear transfer definitely is a viable technique. And the nuclear can go through two hosts. First host, germinal vesicle stage egg. Second host, an in vivo mature egg. The reason to go through in vivo mature egg at that time in 2003 is to overcome the shortcoming, the poor quality of in vitro mature egg. Now, as of 2016, I think there's more and more new technology developed and the technique improved dramatically. And I think we are much more efficient to improve the in vitro mature egg. So whether we still need to do sequential transfer is next research. But important information is that as of 2003, we already have the technology to do sequential transfer, not just the spindle transfer, not just the GV transfer. We can do a series transfer with the same nucleus. Now, I'm going to give you a question. It's a really interesting question. We discussed that when we transfer the embryo into the oocytes in the patient with mitochondrial DNA disease or many diseases, and you already heard the story. And one of the frequent asked questions, the heteroplasmy, and you still have some carry over of mutated gene from the patient egg into the donor egg. And many voices concerned that this mutated gene may still left over, may carry to the mom, which is really not the issue. But let's say this is the issue. Now, how can we solve this problem? It's really easy. We can do sequential transfer. Practically, we can transfer embryo into two host nucleus, and it can completely wash out any residual of a mutated mitochondrial DNA if we want to do it. So this model, even though it was established in 2003, but we already have an answer and a solution for that if this really is a problem, which I really don't think it's an issue. So now let's spend some time to talk about spindle transfer. The video starting? Okay, I'm sorry, same music again. If you don't like, just bear with me for 30 seconds. Kind of boring, same music, same voice, again. That's a good idea. So this just shows the technique of a spindle transfer. Again, first remove the spindles. Spindle. Spindle in the parabiatal space. Electrofusion. See, it's only 5 seconds integrating into the egg. Oh, I'm sorry. I won't let me to do it again. Sorry. I have no intention want you to listen to this music a third time. But it's a very important part at the end I didn't show you, so please, I did not do it on purpose. I have no copyrights about this music. As of today, almost all the published papers in the human egg spindle transfer all use virus. And in the studying the animal, that's why I want to see. This is electrofusion. It's not a virus fusion. Okay, so let's continue. So this is the data which will show that the fertile embryo development. And so as you can see, the blastocyst formation rate and the patient from 35 to 46 is dramatically reduced, even you do the spindle transfers. So to overcome the euploid and aneuploid issue in the human, and we still think we need to go the germinal vesicle transfer. So these slides we're already familiar with. I just want to point it here. So for the patient with a non-genetic disease, and for the patient with advanced maternal age, I think the solution is in this part. Because once they finish the first meiotic division and reach to the metaphase 2, about 85% of the meiotic errors has occurred. And spindle transfer for the advanced maternal age will have very limited utility, even though, and still possible, 15% of patients will be possible to use this technique. And if you pay attention on yesterday one of the slides, and I think by Dr. Monet and or Dr. Mark Hughes from our lab, even with the euploid donor embryos, the implantation rate in the good hands almost 75 to 85%. But with the same euploid blastocyst embryo from 44 to 46 years old lady, the implantation rate is still around 50%. So there's 30% difference even with the euploid embryos. So that means there's some other defect, not to the spindle, but in the cytoplasma. So for that group of patients, I think 15% of patients can benefit from this process of spindle nuclear transfer for non-genetic reasons. So this is just to show all this paper, we use electronic fusion. And this, I want to show next few slides. In the model, we can skip these slides. I just want to show this. Now, if you remember, at an early stage, we made a conclusion that the nuclear can undergo normal genetic process in the host oocytes, and there is no immunological rejection. So this is called autotransplantation. Now, what about the xenotransplantation? And if this cytoplasma to induce normal meiosis is species determined or species specific or not? That's also a very important question to answer. So we did this xenotransplantation study to exchange the germinal vesicle between human and a mouse eggs. So this is a normal spindle in the human oocytes without the micromanipulation. And this, it would take a GV from mouse oocytes, but transfer into the GV stage oocytes of human eggs. As you can see, they show exactly the same spindle as all our colleagues who work in the animal, in the mouse. You know, the mouse spindle is much big. So they are morphologically just like human spindles. Let's look at it from a different way. Now let's do the exactly reciprocal difference. Now we're going to put a human germinal vesicle into a mouse egg. You see what's happened? Did you remember the spindle was very fat and short? Now it's a human. In the mouse egg, the spindle becomes narrow and long. So that means the spindle behavior is closely controlled by the cell machinery in the cytoplasma. And this fact is not even species specific. You basically can have mouse behavior just like humans and have a human behavior like a mouse. Now, so this is also a very powerful research tools. And the clinical application of these procedures is to save the endangered species. And so you can use the surrogacy eggs to put the nuclei of the endangered species and to replicate this endangered species herd. So this is another potential application of this technique. But the information from this study are very important for us to confirm that if we can provide a normal healthy cytoplasma from mouse, not as from mouse, from a healthy eggs, it definitely can help to rescue some defect in the nucleus. And this is just to further show that, as you can see, when the human chromosome, mouse chromosome into the human, it looks like a human chromosome short and fat. And you put the human GV into the mouse egg, the metaphase looks just like mouse chromosomes. So I would like to summarize from today's talk that nuclear transfer is a very useful platform for research, for potential genetic disease, and maybe in the future for certain type of human infertility, maybe mainly related to the female infertility. But the limitation of this technique and the safety of this technique is need to be critically followed up. And just like in vitro fertilization was originally invented in 1978, and we only know the application of IVF is for tubal effect. But today, after 50 years later, and I think only 5% of the time you perform IVF is for tubal factors, and 95% of the time doing IVF for many, many different reasons. So I think the future of this technique is great. But what we can do, I really don't know. Thank you.